the angle between these two signals. And if the angle is 0, so it's perfect, right? So we actually can almost perfectly reconstruct a signal up to only to a constant. If they have a very large angle, so that means the reconstruction is not satisfactory, right? And then actually we can find the similar results to what we set up the guarantees of perfect reconstruction for the dimension invariant blocks. The projection angle actually is still bounded by the singularities of the transform. So we can we can demonstrate that it is actually stable, right? Then when we achieve downsampling and upsampling use this kind of reversible blocks. Here are some results for image compression. So, oh, sorry, forgot to translate it into English. So we actually can achieve the comparable rate distortion performance to existing methods using only about less than 60% parameters using this kind of reversible blocks. And we also make some extension based on this kind of frame, right, to different kind of signals. The first extension is to graph signals, right? So the signals living on a graph. And then we can also use something like the spectrograph wavelet frame to establish a graph convolution networks. It also can extract multi-scale representation, and it also inherits the properties of wavelet, right? So it can be localized in both vertex that corresponding to the temporal domain and the spectral that corresponds to frequency domains. We can also guarantee the stability for this kind of transform. So here are some proofs. So I just skipped it. And this kind of construction can be leveraged for both designed wavelets, right? So we can consider to directly use some existing wavelets, for example, Mayer, Simoncelli, or something like diffusion wavelets. We can also try to make the wavelet learnable. And based on this kind of formulation, we can still guarantee the stability of the convolution networks. And then where we can employ this kind of methods into point cloud compression. And we try to optimize the U frame, so the frame used for reconstructing the signal. For example, we consider nonlinear P Laplacian constraint for reconstruction. And finally, we can achieve better performance than current standards in MPEG GPCC. We can also extend this kind of frame-based methods or networks to spherical signals. For example, for AR, VR, right? And we can similarly develop the so-called anisotropic spherical scattering transform, right? So it's also based on the wavelet frames. And we can guarantee a series of properties, for example, for the multi-scale directional representation, for anisotropic low-pass and band-pass filtering, and for frame for guaranteed stability, and also the rotation invariance and stability to the deformation. Okay, and then I will come into the second part for the variable rate and progressive linear image compression. Actually, there are also some methods, actually many methods, right, to achieve variable rate compression. So we can summarize them into three kinds of methods. The first is the so-called parameterized transform. So the idea is to introducing the you may recall the parameter lambda into different learnable components, for example, into convolution or into nonlinear function, or introduce a fine transformation after convolution. So we can make this kind of components associated with the lambda, right? Then when we're learning the entire model, we actually also adjusting the value of lambda. And the second is multi-scale decomposition. So it's it's a very straightforward idea, right? And the second is to use quantization step to adjust quantization error. So our work is based on this kind of the third idea. But currently, the problem for adjusting quantization step is that we inevitably lose some important information, and we will find a degraded RD performance when we use this kind of method. But we still have, but this kind of method is still very promising because we can just use one model, right? Use just one single transform to achieve variable rate coding without introducing any complexity. So it's very promising for practical coding. And we first make some analysis on the latents, right, obtained by learned image compression. We consider 3 latents, exactly the feature maps obtained in the low, middle, and the high rates. We find some interesting phenomena, right? So you will find we actually will not use the entire channels when we set a low rate, right? For example, here 1 and 19.2 channels here. But for the low rate, we will only use 1/3 or less than a half. And second, you will find that all these occupied channels, they actually have some similar color, frequency, or orientation patterns. So these two phenomena implies that actually it is possible for us to adapt rate using just one single transform. The only problem is that the frequency of the resolution of the channels will change, right? So that's why when we scale each channel using a scaling factor, we will lose many information. So now our idea is very intuitive, right? So we can directly use the invertible transform, right? Because it can guarantee perfect reconstruction. And then we use this kind of reverse blocks to maintain the high frequency details. And then we can scale this kind of latents for variable rates. So this is the scheme, right? Actually, we use a nonlinear downsampling, upsampling, and the reversible autoencoder then to guarantee perfect reconstruction. Then we just use scalar scaling, right? Like the scalar quantization to achieve variable rate coding. Also, because we want to concentrate more information into few channels, right? So we use this kind of hierarchical stacking of reversible blocks. So we can easily reduce the channels, right? Because the channels for each branch reduced after one layer. And here are some results, right? For example, for the RE performance, and we can also use this kind of method to estimate the lambda for rate control and distortion control. And actually, it's accurate in rate and distortion control. Okay, and we can further consider the so-called progressive coding. So that means when we generate one bit stream, we can truncate the bit stream. And each truncated bit stream can provide a reconstructed image of different qualities, right? So that means when the network is dynamic, we just need one bit stream, and then we can truncate it for different network conditions. And we can inherit this kind of idea of scaling, right, to achieve progressive coding. The only problem is that because we want to achieve we want to use truncation to achieve different construction of different qualities, right? So we have to guarantee that each quantization interval, if the one quantization interval of smaller scales should be covered by a quantization scales of large intervals, right? And you will find when we use uniform quantization, for example, in the left, the boundary, right? When we use an even quantization step, or an even scale, the boundary of the quantization interval actually coincides with the quantization center for the finest layers, right? So that means for this quantization center, we cannot determine which interval it belongs to, right? So it actually cannot guarantee the embedded quantization. But for the even scale, this is not a problem, right? We do not have this kind of problem. And when we test its performance, we'll find when we make the scale, right? So the ratio between two adjacent quantization steps, for the even scales, so the performance will significantly drop. And actually, the solution is to introduce data zone quantizer to avoid this kind of problem, right? Because for the data zone quantizer, we have a large interval near the 0 point, right? And we will avoid this kind of problem for both even and order scale. And the next step is just to establish the relation between the uniform and the data zone quantizers, because most pre-trained AIC models is based on the uniform quantizer. We don't want to retrain these kind of models. So we just use the companion function to relate the data zone quantizer to the uniform quantizer. Actually, you will find that for when we transform we convert between data zone and the uniform quantizer. The only thing we do is to change the size of the intervals between the 0 points, right? So it's actually some kind of nonlinear conversion. So we use the companion functions. And actually, finally, that we can directly use the pre-trained models to achieve the equivalent performance for progressive coding. And we can, and we can also extend this kind of method from hyperprior, right? So that means the zero mean entropy model to the autoregressive. So the entropy model has a parameter of mean. So the difference is that when we have a mean, so the quantization step will shift with the mean, right? So it will center at mu, right? The mean value. And what we do is to use a pseudo quantization set to align the code word obtained by a coarse layer and a finer layer. Okay. And the direct effect is that we can just use this kind of quantization method to achieve the scaling, the scalar quantization like the traditional transform coding. So that means we can realize in a very low complexity, just as JPEG 2000 or like BPG. And then we can also extend this kind of embedded quantization to task-oriented AIC, right? So that means we use different quantization to generate a bit stream for different, maybe machine vision tasks for object detection, segmentation, object tracking, because we know different machine vision tasks have different granularity of features, right? Require different granularity of features. Finally, it's some works on the probabilistic entry modeling, right? So when we revisit the entropy model, we'll find we actually the prevailing method is to introduce the so-called parameterized distribution. So for example, Gaussian or Gaussian mixture, right? So that means we have to deterministically find the mean and the variance of the Gaussians. But this kind of math actually is not good for generalization. So our idea is to further introduce a distribution for both the mean and the expectation, right? And the variance of the Gaussians. So we first try to introduce this kind of idea for the mean parameter, right? So we consider to model the distribution of this kind of mean parameter and use the deep Gaussian process regression. And we actually just needed to reformulate the RD function or the RD loss function, right? Using the ELBO, right? Evidence lower bound. And to achieve the rate of RD optimization and this kind of deep Gaussian process regression-based entropy model. And surprisingly, we find that it does improve the RD performance, right? And also enhance the visual quality. So subsequently, we also consider, so can we still model the variance also as a distribution, right? Then we find actually it's very popular now, right? So we find the diffusion process. So we use a diffusion process to model the distribution of both the mean and the scale of the Gaussians. And actually, we can find a surprisingly high performance gain, right, to existing methods. So we just this work is just under revision now. Okay, so that's all the all the contents I want to share today. Thank you.
Thank you, Professor Dai, for the great talk. Yeah, any question from the audience? Any question?
So have you derived any relationship between the downsampling rate with proportion rate?
Actually, we cannot find the specific relation between, for example, when we have one input image, but we actually can set up a energy, right? For example, when we have a input signal with say energy F, then when we achieve downsampling and upsampling, we can find the range of energy when we obtain the reconstruct image. So that's what we can do.
Okay, thank you.
Any other question? Yes.
老师你好，就刚刚就提了一个就 diffusion base 的一个商模型，然后我有点小，就是说它这里 diffusion 是怎样去增强这个商模型的，或者说它在商模型这儿作用是什么？
就是因为我们出发点其实是考虑现在的商模型，它都是比如说我就是一个固定的，比如说多个高斯的这种混合，或者是这种形式，对吧？那么它的每一个参数都是要固定的估出来的。那么我在学的时候当然可以学得很好，但是当我们应用的时候，那么就面临了泛化性的问题，对吧？那么所以我们就考虑我们能不能直接去建立这些均值和方差它们自己的分布。那么所以我们的 diffusion model 是用在这个上面。也就是说，我们通过学出这样一个生成的这个过程，那么当我在训练好了这样一个模型去用到这个比如说实际的编码的时候，那么我给了一个 latent， 那么我就以它为条件输入进去，那么它直接就给出它对应的这个均值和方差，它的这个生成出来这个 sample， 那么我就用它来进行编码。
那就是相当于就是 diffusion 是用来帮助更好的去预测它的均值和方差，是这个意思。
对，是的。
行，谢谢老师。
Let's thank Professor Tai again for the great talk.
Thank you.